let's get started. So first, I want to ask some of you what you think is learning. Why? Forget from the computer science aspect or something like that. Can some of you tell me what you feel is learning? It's quite hard to define, but all answers are welcome.
Trying to understand something is learning.
Trying to understand something. Okay, that's a good one. Let me, I'm basically just going to write things here so that we can, collect it. Did it go? Am I still sharing?
No, ma'am.
It's gone, right? One. Okay, so yeah, trying to understand some concept. Any other answers? Trying to understand and acquire knowledge about a specific topic for the purpose of solving problems or creating new things. Yeah, what you said pretty much covered that. Okay, I will. Oh, okay, this is another student. I'm sorry. I will add that as well. So I guess Vishal and Ashwin answered, am I right? Anybody else wants to give a go? Okay, I will move on now. These are two pretty good answers where you're saying that I'm trying to understand a concept, I'm trying to understand and acquire knowledge so that I can solve problems. But do we learn things just so that we can solve problems? That's a bit interesting. But maybe everything is a problem. I don't know. It's an interesting choice of words. But yeah, I started at Wikipedia, and it's quite similar to the second definition, I guess. And we try to acquire a lot of things, whether it's knowledge or behavior or skills or things like that. So though we use machine learning a lot, I think we have to slow down and think, what is it that a computer is learning? Is it actually learning? It is a machine. How is it developing this ability to learn? Can a computer learn? Or is learning something so human that you can never model it? And how do babies learn? Like babies learn language at the age of I don't know, from 2 to 5. So our computers are not even close, and this is something a baby can do. So what is it we are missing? And our brain has fixed, every brain has same number of neurons, but it learns so many different and variety of skills. So how is that happening? So we'll start with a bit of introduction to machine learning. It might be a repeat from your courses, but I thought it will set the background. So we often think machine learning is like it's a completely different paradigm. We have it's completely different from OOPS concepts or regular programs. But at the end of the day, whether it's a machine learning program or your normal program, they're both coded in the same language. So there's something that makes it different, and we're going to see what that is. The fundamental difference is how we interpret the input and the output. Both of these are normal programs only, but the way we assign value to the input and output makes it a learning program or not. So to illustrate, in a normal program, a computer is just used to compute. You know the algorithm, you're trying to compute something. So if I say finding a square of a number, then I know that this is going to be the input. I know the procedure. I'm going to do power function, and I'm going to get the output. And I'm very sure, given this input, this is going to be the output. So we call it deterministic. Now, in machine learning programs, we have the input and the output, but we are trying to find the model or the equation beneath it. So if I tell find the polynomial and I give 1, 2, 3, 1, 4, 9, then the output is x squared. Now, the point is for a program, the input is just 1, 2, 3, 1, 4, 9, output is x squared. For the program, input is 2, output is 4. But we give the term machine learning to this because we did not know that it was x square and this has modeled it. So it's not so deterministic basically. So in traditional programming, you have the data and the program and you get the output. But in machine learning, we give the data and the output and we get the program. Now, though it is termed this way, at the end of the day, we need to remember that these are our programs which follow the various OOPS concepts we have learned before. So just to reiterate, this is only interpretation. So I just had a video to show that, okay. I wanted to mute it, but it is not happening. So it's okay. So basically with the data, when we learn or do linear regression, we see the parameters adapting. Now, why are we learning now? Do we not know how to program things? Why are we asking the computer to learn? Like if you tell me find the square of a number, I can tell. Why are we doing this exercise? The thing is because real data does not follow models that we are aware of. Even when we know the laws of physics, for example, for driving a car, we don't know how to model driving a car. It is something we learn through experience. And in general, the real world is too messy, and now we have access to enormous data, basically. Now, did we learn from data before computers? Yes, statisticians have been doing this. Statistics, when I was in school, was the worst subject because there'll be this huge line of values, and whenever I added them, I would make a mistake somewhere. But once again, computers are just tools, and most of the maths comes from statistics. And the increased power of the machine is what has revolutionized the world. And I just put a poster of Moneyball because it had something to do with machine learning and numbers for a real world problem. So now that we have some understanding of what are learning programs, what is deep learning? Is it like we have more data? Is it a bigger neural network? Or is it a small neural network with many layers? So it's a combination of this, but the power does not come from each of these individual points. So the greatest advantage, I would say, of deep learning is that it decides what is good for the algorithm. In machine learning, say, if I had to classify, for example, that this is an image of a car or not a car, then I would, as a human, choose features. Say I would detect circles and say there are 2 circles. So number of circles could be a feature. So I would detect features, put them in the feature extraction, and then I would use any of the famous algorithms and get the output. Now in deep learning, what I'll do is I'll just give the image of the car. So I'll basically give a set of pixels with RGB values and give it to the model. And in the model, it will do both the feature extraction and the classification, and we get the output. So this process made it very easy for computer scientists to do a lot of algorithms, and they also generalized quite well, which was surprising because usually generalization is a hard problem. So this is achieved through something known as representation. So what do I mean by that? Now we take this example. We have 2021 represented in Roman numerals and 2021 represented in normal numerals. Now, when the Romans were using this, they found addition, subtraction, multiplication very hard because this representation of numbers is not suitable for such algorithms to do with ease. But the representation of 0 and the decimal system has made calculations extremely simple. So in both of these, we are representing a symbol, an idea of the number 2021. But this representation is far more useful. And that is the contribution of deep learning. It finds out the representation. The user need not come up with the representation. So now we are going to start a bit of math. We've had like 20 minutes of introduction, and at the end of this class, I want you to have a really clear idea of these terms. What is a perceptron? What is a perceptron rule? What is gradient descent? What is stochastic gradient descent? Multi-layer propagation. Multi-layer perceptron and back propagation. Okay. So first we'll start with perceptron. It's derived from the word percept, which means understanding. So we can see it's tying back to learning and things like that. So it's a simple model of a biological neuron. A biological neuron is far more complex than anything in this, that this perceptron is modeling. So the idea that we derive from the biological neuron is that we have a set of inputs that come into the neuron, and it is propagated through the impulse only if it crosses a certain threshold. This is what we are addressing. Now, the interesting thing is a neuron does far more than that. We'll be seeing that maybe at the end of the course of what are the differences between human learning and machine learning. But this is what we have taken. We take multiple inputs, single output if it crosses a threshold. Yeah, it's just stated whatever I've said now. So I'll start with a bit of history. This is interesting for me because the perceptron design started in 1943 with the McCulloch-Pitts neuron. Now, to put it in context, the first computer was invented after that. So people were thinking of a lot of ideas, and you need to remember the 1940s were the time between the two world wars, and whenever there's a lot of historical and political activity, there's a lot of, sadly, research to science. It should be the other way, but that's how history is. So to put it in an actual design, there was a mechanical machine developed by Frank Rosenblatt in 1958. Once again, it was not for a computer. It had gears and things like that, which could mimic this neural network. Now, what happened is, we'll be seeing in this in this lecture itself that they suffered from one flaw that made it very unpopular compared to other algorithms. To overcome that, in the 1990s, the multi-layer perceptron came along, or the artificial neural networks, whatever you want to call it, which is basically a network of these perceptrons. But still, they could not achieve the level of success that the other algorithms were having. For example, in the 1990s, it was all like SVMs and other statistical methods. But in 2010, the things started shifting, and because we had more processing, more storage, we realized that for such a system, ANNs were quite powerful. And that is like the beauty of research. You never know when your thing would be useful or something like that. You just keep reporting whatever has been done. So now we'll come to what exactly the perceptron is. As I said, you have multiple inputs, input 0, input 1, and then they are weighted. By weighted, I mean here what will come is weight 0 into input 0 plus weight 1 into input 1, and then you have output only if it crosses a threshold. So we'll be seeing an example. So this is the mathematical thing. So if weight 0 into input 0 plus weight 1 into input 1 is more than the threshold, then the output is. If it's less than the threshold, then the output is -1. So to simplify this notation, we just sum over all weight into input and say that, okay, if it is greater than or equal to threshold, I'll say it's +1, and if it's less than, I'll say -1. Before this, we had the McCulloch-Pitts neuron. The only difference is that the input had to be binary. Perceptron doesn't need such restrictions. Now, we will shift to vectorial representation because our data is going to be a set of numbers. So if the weight vector is W0, W1 to Wn, then our input vector is X0, X1 to Xn. W0 into X0 plus W1 to X1 can be either represented as the dot product of them or W transpose X. If you do W transpose X, you will get that. So this will be like a vector like this, then you'll have a long vector like this. Then it'll be W0 into X0 plus W1 into X1 and so on. You'll basically get this expression in both these representations. Now we'll come to a few examples. So what does the computer need to learn? It needs to learn what are the weights, what is the threshold. So if the inputs are 0, 0, 0, 1, 1, 0, 1, 1, this is for an AND gate. You know, AND is true only when both are true. So it's going to be -1, -1, -1, 1. So what should the weights be? So if it's an AND gate, think about it this way. So it should, if both these weights are 1 and 1, just go through what will happen. It will be like 0 plus 0. First it will be 0. That's not accepted. Then 0 plus 1, it's not accepted. 1 plus 0, it's not accepted. 1 plus 1, 2 should be accepted. So you keep the threshold as 2. So whenever the sum is done, you will get many numbers. Only when it is 2, it is going to give a positive output. Is this clear?
Yes, ma'am.
Okay. I will. So yeah, then can someone tell me what the weights should be for an OR gate?
You can keep the weights as 1 and 1, but change the threshold to 1.
Yeah, that's about it. So yeah, that's what an OR gate would be. So you've got the idea, or you probably had the idea of this before. And yeah, so what exactly are we doing in a perceptron? So in this, this is called a discriminative model, where we are trying to find um, the model of the difference. Basically, I have positive and negative, and I want to find the change, basically. Generative models model the entire data and say which belong to the positive and which belong to the negative. So instead of modeling the data, we only model what is differentiating them, because that is what we're finally interested in. So this is a discriminative model, and we want to build this plane of separation. And because our data is usually in higher dimensions, we call this a hyperplane. So now we come to the perceptron learning rule. Now, for simplicity, what we do is we bring the threshold also into this multiplication, and we put a -1 here because it comes to the other side. Similarly, we also add a bias. Yeah, I'll have a poll at the end of the class, like if anybody wants to discuss bias versus variance, overfitting and all that. I've not planned it for this lecture. So we'll come to the perceptron learning rule. What do? We basically update the weights a certain number of times such that it follows this rule. Basically, eta is a training rate, and t minus o is training minus output, and xi is the input. So what does this mean? So if your algorithm gets the output correctly, t minus o is 0. That means the weights need not be updated at all. So wi will be wi only, no weight updation. If it guessed it wrongly, there are two cases. Let's take your training is 1 and your output is -1. That means my algorithm is guessing something very low. the training is 1, but output is -1. So I have to increase it. So 1 minus of -1 will become 2, so weight has been increased. Whether I wanted to increase by q or not is controlled by this eta, which is the fractional value. Similarly, in case 2, we have -1 and 1. Again, your algorithm is getting something high, then actually a low one is required. So now I have to reduce it. So it will be -1, which is -2, and weights are decreased. So this is the intuition behind the perceptron learning rule. If you assume eta to be 0.5, wi is wi plus xi, because you'll get 2xi, and by 2 you'll get plus, and similarly minus xi, you'll get this. This is often also told as the perceptron learning rule. Both versions are fine. It just means if this eta has been taken as 0.5. So now we have understood why t minus o is required. Now why are we taking this xi also? Why is it a function of the input? Because we said we're only interested in the difference, right? And that's because our final expression has wi xi. Imagine that our wi is, imagine our xi is 0. No matter how I change the weight, it's not going to help. So the weights, the contribution of weight to the threshold is dependent on the input. And as I said before, we are learning the threshold as well because we have brought in the threshold into the weight vector. So here we have some mathematical proofs that we will not be looking at, that if eta is sufficiently small and data is linearly separable, then it will converge. But we will look at it for some time, that why data is should be linearly separate. Now this was the limitation I said that caused a lot of unpopularity for perceptron. There were many papers written on how it will not generalize because of this flaw. Now why does it require data to be linearly separate? What are we modeling? We are modeling w1x1 plus w2x2, something like that, which is basically the formula of a line, y equal to mx plus b. So we are having an equation of a line. Obviously, our separation is going to be a line only. So this is what it's going to do. So we will be able to model for and or, but we will not be able to model for XOR. I'm sure many of you would have come across this example as well. And this is the reason, because what we are modeling itself is a line. So there is no way we are going to be able to do something like this, which is like it's like a hyperbola that goes here and here. So now we go into the next algorithm, which is gradient descent instead of the perceptron learning rule. Now the perceptron learning rule will not converge if it is less than, if the data is not linearly separable, but the gradient descent method will at least give the best approximation for the classification problem. It also cannot help in classifying if the data is not linearly separable, but at least it will give some near value. So what are we doing? We already said that we are going to find the separation. Now, how will we find the separation? We want to minimize the error, the difference between the training and the output. So we directly model that. Instead of finding a line that will separate using this trial and error of updating weights, we say let's find the best possible such that the error is reduced. So if I have a data set of B points, and then we see training minus output, what is the error, and we take the square so that it's differentiable. So these are taken from Tom Mitchell slides, and I'll be giving a link to that as well after this class. So if these are the weights W0, W1, then the error would be like this. So we know that when you have, a square function, it's like a parabola. You might have learned it in like engineering drawing or something like that. And yeah, if you want some pointers to that, I can send some materials. And we have several weights. So we take the partial derivative with respect to each of the weights. And we have the same training rule, which is that we want to update the weights with the gradient of the error, not. Um, so we were sort of doing that in Perceptron learning rule, where we said t minus o times xi. And if you see, it happens that because the value is w on x1, the expression is quite similar. So we have the derivation here, which is that we have the difference. We use chain rule and get 2 PD minus OD and the difference of this. Now, we know that the output is W dot X. So when we differentiate with respect to weight, it will become minus X. And this, as we know, it's very similar to the perceptron learning. The difference is that here we are summing the errors over the entire data set. There we just saw Wi, Xi, that's it. So that is the difference. And how, as an algorithm, you will code this into the system is that you will first initialize all the weights and to some small value and until some termination condition. Termination condition could be like number of steps, which is usually what is done in practice, or some acceptable error limit. This we don't do usually because you can never guess what is an acceptable error for an algorithm. We usually say, okay, 10,000 steps, you do gradient descent or something like that. So then what you do is you initialize delta Wi to 0. And then over all the training examples, you will see what is the output and measure this change. And you will sum this change over all the training examples. Now, this is also called like batch processing because over the entire data set, you are measuring this. And you can see it's very similar to what we saw in Perceptron, except we're doing it over the entire data set. And then after you have summed up all the delta Wi over the training examples, you do Wi plus delta Wi. So over all xi's, you have summed it and finally the weight is updated. So this is much stronger than the next version we are going to see, which is the stochastic gradient descent. So in stochastic gradient descent, that is actually quite similar to this one, Perceptron. So here in every training example, we compute the gradient and then directly we update the weight. Here if you see, we keep updating the weights, we keep summing it up, and then you do Wi is Wi plus delta I. But here what you do is you say delta Wi, and then you just push this back here and you keep repeating this thing again and again. So what happens is you remove one for loop. Now imagine if you are calculating the complexity, there's a for loop here, which is like you keep iterating this. That's one. There's a for loop here, which is second, which is over the entire data set. And you have a for loop here, which is the various weights you have. So it's a 3-level for loop. And I'm sure when you have for loops at this depth for a large data set, it is very expensive. So we have an approximation where you just get rid of this for loop. So you get rid of this for loop and you put it here, basically. So that is your stochastic gradient descent. So that brings the number of for loops to 2. It is still expensive, but much better than the gradient descent one. And it is not as perfect as gradient descent, but it is a good approximation. Any doubts till now?
In the stochastic mode, so like you will update for like each training example, right?
Yeah.
but you will also have like a total number of iterations. So like the number of updates will be total number of iterations into the number of training examples.
Correct.
Is that okay?
Yeah. And in the normal gradient descent, you will have into the number of weights as well. That's what. So stochastic sort of means like random, loosely. So it's like you're taking a guess at every time. It's not perfect, but yeah, it works in real time. So I will now move on to multi-layer perceptron. So multi-layer perceptron, it's a very simple extension of perceptron, but it overcame a lot of the problems that perceptron has. So what it does is, a perceptron would have multiple inputs and a single output. So now if I club the perceptron such that it has only a single input and multiple outputs, that is the idea. So you have single input, multiple outputs, and they're all connected. So I have layers of these nodes, and it is, we call this like fully connected graph, right? Where every node is connected to every other node, but only among the layers. It's not like this node is connected to this node, which is not true in a fully connected. I think it's called a bipartite graph or something, which is basically among different sets, it is fully connected. So you have multiple inputs, and then now you have weights across layers. So if this is node 1, 2, 3, 4, 5, 6, 7, 8, 9, you have weight 1, 5, 2, 5, 3, 5. You also have 3, 6, and so on. So now you have a lot more weights, and you have something called a threshold function. Before we were just having a linear threshold function. That is, we just chose a value for threshold. Now we are going to introduce non-linearity as a function. So no longer are we having a linear function. So issues of linear separability are not there. So what is this activation function or threshold function? Ideally, we are trying to have a differentiable function. Once again, we differentiate so that error is minimized, and you can compute minima, basically. So what the threshold function does is, it's also called a squashing function. So you have a large set of values. So what it does is, it makes the values between -1 and 1. So -1 and 1, or 0 and 1. This is basically 0 and 1. And it's only at this you have between, say, 0.5, 0.25. But for a large set of values, it is either just 0 or 1. So it pushes it towards the classification. And how do we get that? This is one of the functions. We have various activation functions. One of the functions is sigmoid function, which is 1 by 1 plus e power minus x. So when x is very high, it will become e power minus infinity, which is 0. So that's 1. That is this part. And when x is very low, it becomes minus infinity, or e power infinity, and 1 by infinity is 0. So this is 0 and this is 1. So this is our squashing function. Now the nice part about sigmoid function is, when you differentiate it, you get back sigmoid itself. We know that e power x, when we differentiate, we get back e power x. So you can do this after the class, and if you differentiate and see, you will see that this holds. Where 1 by 1 plus e power minus x, if you differentiate, you get this, which is in terms of the sigmoid function itself. Now, I'm just summarizing whatever we discussed. That is, non-linearity is achieved through an activation function. The activation function pushes it into two states, or it's like the squashing function, and it's differentiable for gradient descent. Some of the other functions we have is like tan hedge, and inverse tan hedge, and so on. So these are also squashing functions. Tan hedge squashes it between -1 and 1. That is the difference. Now, I'll give a small intuition behind why multi-layer perceptron works. So it's basically um, because you have a different layer, you have more room for interpretation. Imagine if I was giving two inputs here and I had four internal nodes. Each of the nodes can represent what the output should be for this combination. Sorry. So if I have 0, 0, 0, 1, 1, 0, 1, 1, then the weights can be such that if my input is 0 and 0 from these two, what the output should be. That is why the multilayer perceptron is able to come up with better representations. There's more room for representation and is also not linear. We are not just passing a line. Because of the sigmoid function, we are giving a differentiable non-linear thing. And you have to remember the activation function is applied at every node. So because of that, there is a sum of nonlinear functions. So it's extremely complicated. So it's not going to be as simple as we saw here. It's going to be like up and down and so many things because you have so many nodes and so on. But what we are losing in that certainty, we are gaining in the nonlinearity and complexity. So now we come to backpropagation, which is the last part of this class, which is basically how we learn the weights and the threshold. Okay, we don't have threshold here. How we learn the weights. So we need to find weights that will minimize the error. As usual, we are going to do the gradient descent method. So the idea is you propagate the input values forward and you propagate the errors backward. Because we propagate the errors backward, we call this backpropagation. That's basically. So to understand the derivation for that, first we will see what is the derivative of the sigmoid function. So I basically have to differentiate the error with respect to the weight. And the error is going to be the same thing we discussed for normal perceptron, which is basically differential of the error based on weight 0, weight 1, weight n, and so on. So let's take it for one single wi. And you have the sum over the data set, td minus od, the whole square. And you have a half conveniently so that you can cancel the 2 and 2 that comes. And then we apply chain rule and we reach here. This td minus od we had even in the perceptron example. But od at that point was simply w dot x. So when we differentiated, we got x. In this case, however, we are saying that our OD is different. What is our OD? OD is basically sigmoid of whatever was the previous sum of the previous inputs. So, for example, when I come here, my OD is going to be sum of this, sigmoid of that. When I come here, sum of all these four, sigmoid of that. So that is my OD. It's no longer WIXN. Yeah. So now I have to differentiate this with respect to WI. How? What do? I again apply chain rule and I say differential of OD with respect to net. Net means the sum of the previous inputs, and then the differential of the sum to the WI. So first we'll do this part. So be with me that differential of error to weight is split into two, which is basically differential of the output to the net and the net to the weight. Now, differential of output to the net, we know it's sigmoid of net compared to net. Now we know sigmoid of net is sigmoid, the differential is sigmoid of net and 1 minus sigmoid of net. But the beauty is the way we have designed it, sigmoid of net is OD. So in our answer, we'll get OD into 1 minus OD. Now, differential of net with respect to WI is going to be the same thing. It's going to be W dot X. So that we get that again. So now finally, the differential of the expression with respect to the weight, we get this part is here, and this part is here, this entire expression. So instead of just TD minus OD into XID, because of the sigmoid function, we have this extra term. And this is how back propagation works. So you keep this term in mind, and you will be able to appreciate the algorithm. So what does the algorithm do? Again, we initialize all the weights to small random numbers, and we input for every training example in the data set, we input some value. And then at each of the output units, you will, okay, so the way the inputs are at each of the output and the hidden unit. So we call this layer the output unit and this layer the input unit. It's different. I'll be showing how. So at the output unit, we saw it was 1 minus OD into XID. But instead of XID, you will be using the output itself. When you work this out, you will get what I'm saying. It's quite hard to tell over this. So in the hidden unit, you have this O into 1 minus OH. And for the input, this Xi is going to be sum of all the previous. So that is the sum here. So basically in the output unit, you just have the sum of the previous. Here it is like weight into the sum. So yeah, when you work it out, you'll get it, and you can like mail me later on. And again, we just do a stochastic version, I guess, where you update every weight, and it is the same thing. Eta into this delta J is either, if it's output unit, it would be delta K, or if it's hidden, it's delta H into Xij. Basically, what it means visually is I'm going to give the number multiplied by the random weights, and then I'll get here an output. So now once I've got the output, say I got an output 3, but the correct one was 0 or something. So then this error, what I had was like 3. I'll propagate it back and say, okay, look, the error for these were 3. I know what the differential is. So from that, I will derive what the weight is. And I'll keep updating the weight backwards. So this I'll do again for a number of steps. Maybe like 1,000 or something like that. Depends on the data actually. And I'll move on. So what does this mean? In deep learning, a large number of like deep layers and access to long data has brought in complex representations and non-linearity that could solve a lot of these problems. So we will be seeing different flavors of these multi-layer perceptrons. And theoretically, we have something called the universal approximation theorem, which gives us a guarantee that any nonlinear function can be approximated by an MLP. But the problem is we don't know what real world problem things are, right? So we don't know how much data is required for one particular thing. So I just gave a set of like terms when you can like revise and things like that. So to summarize, we went through what a perceptron is, what a hyperplane is, what linear separability is, what generative versus discriminative models are, what is the perceptron learning rule, what is gradient descent, what is stochastic gradient descent, what is a sigmoid neuron, what is multi-layer perceptron, and what is backpropagation.